equations and groups defined by algebraic difference equations. And so the main result I'd like to speak about is the following theorem. It says that basically says that the difference ideal of all difference algebraic relations among the solutions of a linear differential equation is finitely generated as a difference ideal. The difference ideal, so I just write sigma for difference, the difference ideal of all different algebraic relations among the solutions of a linear differential equation is finitely generated. Finitely generated means finitely generated as a difference ideal.
As opposed to the usual as a perfect ideal.
Yeah. Okay, and so first, that's the main result I want to speak about. And so I'll try to make this more mathematical. But first let me...
Is it part of some sterile graphs then?
Not really. I think it's...
So that's a special property.
Yeah.
Like for differential algebraic groups, we can say something about it finitely generated. So there are some cases you can, we can say that already.
Yeah.
So
it's not the case.
So yeah, so that it basically is so not any. So these difference ideas which occur as those relations ideas, they have special properties, and one of them is that they are always finitely generated as difference ideas. Okay.
It's a sigma finitely generated.
Yeah, finitely generated as a difference idea. Yeah, finitely sigma generated.
Since it's an ideal of difference polynomials vanishing on something, it's in particular, it's transformally prime, I guess.
Yes. Yes.
Good.
Okay. So I'd be more precise about what is the difference ideal we're actually discussing. But first of all, let me start with some the examples of elements in those ideas. So just with some. So this is concerned with the sigma algebraic relations among the solutions of linear differential equations. So let me just give some examples of those sigma algebraic relations.
By the way, so is the same statement true for a different algebraic group?
For different algebraic groups? Yeah, so that's sort of a key point. That's the proof. Yeah. I mean, it's some back and forth. So I'll explain the details of that proof in the talk.
Okay.
Yeah, so that's where we're going.
So they're better off than we are.
And I guess you are assuming that sigma and delta commute.
They commute up to a factor. Yeah.
For differential algebraic group.
Yeah.
For linear differential algebraic group it is. Yes.
Okay, so let me just start off with some examples. So if you look at Bessel's differential equation, yes. So we're interested in difference algebraic relations among the solutions of linear differential equation. So that's the linear differential equation. It's Bessel's equation, and there is a very well-known relation satisfied by the Bessel function of the first kind. So J alpha is the Bessel function of curves of the first kind. It solves this differential equation and satisfies this relation. Now you have the shift in the alpha. So this is not an algebraic relation. This is just a difference algebraic relation. Okay, so this is just an example of the type of relations we're interested in. But there's a lot of
So for every alpha, J alpha is a solution of the equation above?
yeah, but think more of like a generic alpha. But this is true for every alpha. So this like
so this is not exactly a.
It's a family of equations he's talking about.
Well,
So
take a generic
I
alpha.
see. So I see. So your sigma is acting by taking j alpha to j alpha plus
Yeah, like
1.
that would be sigma squared here. Yeah, exactly.
Okay.
So okay, I'll say what delta and sigma is in a second. Okay. Yeah. So if you want, okay. So if you want to see the delta sigma field right away. So here the derivation would be just the derivation with respect to x, and sigma would be the shift on alpha. So sigma of x alpha is f of x alpha plus 1. Yeah. Okay.
And this j function is rational in x and alpha.
You can, if you want, you can write down some formal power series
Okay, it's the base field.
expression.
Okay, it's the base field. Okay, sorry. Yeah. Okay.
Okay. So also some trigonometric identities can be interpreted as different algebraic relations among solutions of linear differential equations. For example, if you take the simple equation by Brabham plus y equals 0, so here you have the sinus and cosinus solutions, and then there is the double angle formula. So for the cosinus of 2x, you get cosine of x squared minus sinus of x squared, and the sinus of 2x is 2 times sinus of x times cosinus of x. Okay. So again, these are not really these are not algebraic relations. So the usual Galois group does not see these relations because you have the 2 here, and this operation with multiplying a variable with 2 is encoded in some by using sigma, by using a difference operator.
But you see, so it's an example number 2, just naively, when you apply sigma that rescales, the coefficients are constant. But what you actually have in mind is that sigma doesn't commute with the derivation. So when you actually apply it, you get something new. Right?
So it commutes up to a factor. So here the natural base field would be say Rx, right? So the derivation would be derivation with respect to x, and sigma would be just rescaling the 2 with the 2, and so it's not quite true that they commute, but they commute up to a factor of 2. So delta, so they commute up to a factor of 2. Okay.
So the action of sigma of sigma on the differential equation is not just by applying sigma to the coefficients. It's more complicated, depending on the relation between the sigma and the derivation. Because otherwise you would not be able to see those relations.
Yeah.
If you apply sigma, you get the same differential equation.
Mm-hmm.
Sure.
Kind of, it's. See the point?
Okay.
So the sigma will transform this to a new differential equation. Maybe we'll
Yes.
calculate it what it is for the example.
Well,
Maybe.
you're differentiating
Well,
twice, so you
it
have a factor
seems-
of 4 coming out.
Yeah, so that,
Yeah.
that will.
Yeah. Mm-hmm.
Okay.
Mm-hmm. Okay.
Because this is just my comment is because we're used in the parameterized theory to see if the equation has constant coefficients, then you say that
Yeah,
okay,
it's
it's
different.
independent,
Yeah.
but it's more complicated when they don't commute.
Yeah, there's a tricky thing with the factor, and so the 2 has to come in at the right place then. Yeah. Okay, but so here the main point is here just to see, okay, you have these 2 solutions, sinus and cosinus, and there is some relations between them which can expressed using the sigma. Okay, so these just 2 examples. There's lots of other examples. For example, like Chebyshev polynomials or hypergeometric equations, and so there's a very formal algebraic setup to study this type of relations, which is which is what we call the sigma Picard-Vicieux theory for linear differential equations. So it was developed together with Lucia Di Vizio and Charlotte Hanouin a couple of years ago. And so the basic setup is that you have a K at the sigma field. This means you have a derivation and an endomorphism sigma, and we assume that they commute up to a factor, so that the sigma is, say, some constant h times sigma delta, and so I'll also assume that the characteristic is 0 here.
And when you say some constant h, do you mean an element of k, or do you mean an element of k such that sigma k is k and
Yes,
delta
an
k is
element,
0?
an element of k.
It's scalars.
And do you make any assumption on what sigma and delta do to h?
Yeah, okay, so maybe we want it to be a differential constant. Yeah.
So do you or do you not?
Yeah, in the paper we do that. Yeah.
Okay.
You're not sure yet now. If you
Yeah.
Okay.
I mean,
Okay. Okay.
I didn't want it to make it too technical, so okay. Yeah. Okay. Yeah. So just assume it's a differential constant. Then just to be safe. Okay. Then it definitely works. Okay. Yeah. So I mean, there's in most in the examples it usually is. The example of redolence, we consider it always was a differential constant.
It doesn't have to be.
Say it has to be. Okay.
Oh, okay.
Yeah. Okay. All right. Okay. So the first thing we need is a place where the solutions live, and this place is called sigma Picabis U extension. So we're gonna study now. We're gonna study differential equations over the delta sigma field K, and so where A is some n by n matrix. Okay, and we want to understand the difference of algebraic relations among the solutions to this differential equation. Okay, so the first thing we need is a place where the solutions live, and this place is called a sigma Picabis U extension. And that the sigma field extension L over K. So, and then the sigma field extension, it just means that the field extension, which also comes equipped with a derivation and a sigma such that the delta and the sigma on L extend the delta and the sigma on K.
So the constant H would be the same?
Yeah, the constant will be the same.
Yeah.
Yeah.
Okay.
Constants and fixed points. Constants of delta?
Oh, I mean, you're asking about the H?
Yeah.
Yeah, the H will be the same. It has to be the same. Yeah.
Okay.
Okay. It's a sigma Picabis U extension. So for this differential equation which we are studying, there's two conditions that need to be satisfied. So first, we want to have a fundamental solution matrix. So there's an y in GLN of L such that y solves the differential equation, and also L is generated over K as a difference field by the entries of Y. Okay, so this symbol here means generated as a difference field. So it's not just generated by the entries of Y as a field extension, but you can also apply sigma to Y. You can apply all the higher powers of sigma to Y. So this is typically not finally generated as a field, but it's finally generated as a difference field. Okay. So that's the first condition. And the second condition is that you don't have new constants. So that's really the same as in the usual Picabis U system.
And everybody other than me is happy with y being both a variable and a particular solution matrix.
Yeah, so this is a small y if you want, and this is a capital
Oh,
Y.
okay.
Okay, so maybe
But you don't have a condition on the sigma constants.
there's no condition on the sigma constant.
No,
Yeah.
because they're just giving you the relations.
Okay, so that's the definition. And whenever you have a sigma Picabis U extension, you can also consider the sigma Picabis U ring which is just the K sigma algebra generated by the entries of y and 1 over the determinant of y. Okay, so again, here you are allowed to apply powers of sigma to the entries of y and to 1 over the determinant of y. And then you form the K algebra generated by all those elements. And because delta of y equals ay, you'll see that this is actually also a differential ring. So this is this is a delta sigma ring, and this is what we call the sigma becomes 0 ring.
And is there any hope of any kind of uniqueness or canonicity?
Yes, so there is up to base extension, the sigma becomes 0 extension and the sigma becomes 0 ring are unique.
So no,
Yeah,
no,
so it's
no assumption on being algebraically closed or anything?
yes. So if you like, let's first discuss the usual Picard-Bézier theory. Then, in the usual Picard-Bézier theory, if you don't assume your constants to be algebraically closed, the uniqueness statement you can make is that after, like, if you have 2 Picard-Bézier rings, then after extending the constants, they will become isomorphic. So you can find, like, if you have 2 Picard-Bézier rings are 1 and 2, and if little k are your differential constants, then what you can show is, okay, there is some finite extension k prime of k such that when you go up to k prime, these two things become isomorphic. Okay, so that's the uniqueness statement for the usual Picard-Bézier theory. And so the uniqueness statement for the sigma Picard-Bézier theory, it's actually a bit more complicated because you cannot do it just with field extension here, but you can do it with something which is very close to being a field extension. So something which is very close to being really just a finite algebraic field extension, so like a difference analog of a finite algebraic field extension. And in fact, so this, you can do it with K being a finite direct product of fields, and which is simple as a difference ring. Okay, so you can do it with some K. But actually, so even if K is model of ACFA, so if K is difference closed, then even then it's not unique, it's only unique. So then there's a sort of different way to reformulate the uniqueness statement. What you can prove is that there exists an L such that these, not just that the sigma Picard-Bézier rings are isomorphic as sigma to the power L delta, so K, sigma to the power L delta ring. Okay, so they might not be isomorphic as sigma algebras, but after going to some power of sigma, they will actually become isomorphic.
And the power of sigma depends on the rings, on the equation, on the combinatorial data in the equation.
Yeah, in some sense, it's sort of, yeah, it depends on the equation. Yeah.
So it depends on the equation,
not,
but independent of the rings?
Yeah, I mean, so the rings only depend on the equation. So.
No, what I mean is I can imagine that given an equation, for any 2 Picard-Bézier rings, there exists an L that makes this work, but there is no upper bound. Can you find an L that works for all rings for a given equation? Or, of course, as somebody to my left is going to ask, can you find an L that works for
Well, the question
I guess
is of particular size.
of particular size, so I guess depending just on the n.
I wouldn't know. I wouldn't know how to. Yeah, so I didn't think much about the meaning of the L. I mean, we have examples which shows that you cannot always take L equals 1, but that's about it. And so this sort of so this uniqueness statement comes out of this one, and it sort of comes out of this one because you can show that you can choose K prime to be like the direct. So if K is difference closed, then K prime has to be the direct product of K's with sigma permuting the factors in a cyclic way. So that's sort of where this comes from.
Yeah, so
And,
the question
so-
becomes how many factors do you need?
Yeah, so that's the question. How many factors do you need? And yeah, I mean maybe like if there's something, assuming, yeah, I guess if you would know that like if your capital K is algebraically closed, or if you would know something about the relative algebraic closure of K inside R, that would sort of give you a bound on this type of. So it's sort of if you want, it's sort of so this type of problem which forces you, which gives you this factor. It sort of comes from the core of the extension. If you're probably the only person who ever heard that word in a room before, so it sort of comes from there.
Yeah, but no, this is all about the formalism, okay? But it's about some algebra. But how about okay? So people ask you about the relation between functions, among the functions, so sine and so on.
Yeah.
Are you sure that this is exactly the can capture the relations among the functions?
Yeah, I mean, in practice, there's a canonical choice for R, and you just work with that R, really.
No, I mean, what does it have to do with functions, with solutions that are functions? With some analytic properties.
Yeah, that's what I'm sort of saying. Like if you start out with the rational functions, yeah, so you'll find your solution just in formal power series and just work there, and that's it. Like you don't worry so much about the like you always have a, so in the concrete example I'll always have a concrete R, right? Like you have the concrete functions.
Yeah, but
Yeah, but what happens if you're looking at a setting where it's not unique, so you have a relation involving an F iterative sigma and an mth iterate for some other one?
Yeah, well, I mean, in practice, as I was saying, so you'll just go for one R, and okay, there might be another R, and well, it's not so different from the R you're looking at. So,
for instance, when you have this, so here you model by maximal ideals and so on of some sort, but don't you produce more relations that actually exist for functions?
Yeah, but that's usually not the problem. With functions, usually what the hard part is to find potential relations, and once you have an exhaustive list of those, checking whether or not they're true is the cheap part.
Okay, so that's how you're going to apply. So your algorithm at the end might produce more relations that actually exist, but then there will be some filtering procedure that will throw out the relations that actually don't occur. A customer wants to know about functions, not about...
Yeah, but I mean, if you have concrete functions, your R is fixed, really. Okay. Why don't you like that?
The Yopika extension might be not as
What do you mean your? I mean,
if Yopika extension. So suppose that even when it is unique, it might have more relations among the solutions that actually exist among functions.
I mean, so you're distinguishing between solutions and functions, or what? I mean,
He's
so
talking about the formal solutions
Between
versus
solutions and
the functions that you. So maybe one thing that
Oh.
could happen is the relations amongst functions, amongst solutions that you find are going to depend on your initial choice of what sigma does. So maybe for sine, you started looking at f of x and f of x plus 1, and you found no solutions. But then if you look at f of x and f of 2x, then you find relations. So that sort of thing might come up. But otherwise, I think it should be
I mean,
helpful.
so in any case, the Picabia rings are always very close. I mean, it's only a very slight difference between the like the sigma dimensions and all the invariants you can think of are the same really.
Okay. So I guess the issue that I have in mind comes up more when you start not with a differential equation but with a difference equation.
You know, like in sequences and functions.
Yeah. Well, so if you replace the original delta by some automorphism.
Well, that's different. That's an entirely different story then.
That's different.
Yeah. Okay. So let's finish worrying about the uniqueness. Okay.
Yes.
And
Just ask one more.
Yeah.
So, I mean, the sigma, of course, is given. And the Picabia ring is generated as a sigma
yeah.
algebra. Would it be in some cases that you have, so this is maybe an R1, and maybe in some cases R2 would be generated by sigma square. It's almost some question that you were looking at last time. I mean, so suppose instead of sigma, I replace by sigma square.
Okay. I mean, you can do that like from the very start. Like if you have a delta sigma field, like put a square here.
No, that's not the question. The question is you're given a sigma. You're given a differential equation, right, where there is a parameter of obviously, right, an alpha. How do you know what? I mean, you're given a sigma.
You choose it from the start.
Or you choose.
It.
See,
Yeah.
the thing
Yeah.
is, when
You start
you
with a
take
delta
the
sigma
equation
field.
first,
Like if I give you that
then you
equation.
find the sigma so that this thing work out,
Yeah.
or
Equation doesn't.
Yeah. Like
or that the sigma is already given to you and you want to see whether you can find any relation with
The
respect to
sigma-
that sigma.
The sigma in K is already given to you,
Right.
and the sigma in R extends in some.
Extent, right, in some
In some-
Yeah. In some way.
And I guess part of the non-trivial claim is that there aren't that many ways to extend it.
Yeah. I mean, like if you're given the differential equation with some parameter alpha, you need to decide how you want sigma have be acting on that parameter.
Of course.
For example, you can act by adding one or by scaling or whatever. You need to fix the type of relations which you want to consider.
But still,
Yeah.
Bill's question, as I understood it, was if you replace sigma with some iterative sigma,
Yeah.
you may now pick up some periodic behavior that you didn't have for sigma.
Oh, if you have some relations for
And then
sigma
it's
squared,
just- you have a
it
different
also contains the sigma. I mean,
Sigma
Yeah.
knows about
you
sigma
won't find anything new by doing that. You lose some information. Like if you replace sigma with sigma squared, you lose some
No,
information. Just a little.
it's the relations that you're going to generate a sigma ideal that might always involve sigma squared, for example.
Yeah, that might
Yeah,
be the
but sigma
case.
is aware
Right.
of that, so that's not a
So
problem.
you'll be
That's
able to
still a sigma
detect that.
field.
Yeah. You'll only find the sigma squared relations then. Yeah, if you only care for those. Yeah, you can replace sigma
See,
by
the thing
sigma
is that
squared.
if I'm given just an equation like that,
Yeah.
like Bessel's equation,
Yeah.
how do I know that my signal should be sigma alpha equal to alpha plus 1? And how do I know that in the
Oh, yeah, that's
y double prime plus
Yeah.
y,
Oh, yeah, that's.
then
what you have to-
I have to know that it is.
Yes.
I don't, I mean, how do you decide? I mean,
Yeah.
You're a mathematician.
Yeah. Yeah, I mean that's
No, no, I mean, that's-
yeah.
No, it's a little bit.
No, I mean,
No, in a
that's
way,
important
it's
to
a
the
little
algorithm.
cheating that you already know the
Yes.
Bessel equation has this property and you
Yeah.
know sine and cosine has this property.
Yeah.
But if I just give you the system, all right,
Yeah.
Then my
with
group,
no sigma, in fact.
then Michael will try shift sigmas, and then he'll try scaling sigmas.
Yeah.
And then he'll throw up his hands and say, there's no way this could possibly be a nonlinear dynamical system.
Yeah, and you
That's
can
the
also
only
try
kind of
alpha.
isomorphism that you can name.
You can do also alpha to alpha square or alpha to some
Yeah.
power, for example. Yeah.
Yeah.
But I mean that's some variety, right?
What's the point of that? What is this you wrote, the inclusion? What is this?
Oh, this
We're
is
just finding solution.
find a
It's
sigma
isolation
picabis
power series.
ring in there.
Square root.
Yeah, finding solution there.
Yeah,
It's, it's power series. You can always expand it power series, right? Not mining convergence, of course.
I'll just erase it, okay?
Convergence.
Yeah.
No convergence.
No convergence.
Okay, so that's the sigma picabis ring. Recall the original theorem we wanted to discuss
Okay, yeah.
is that the difference ideal of all difference algebraic relations among the solutions of a linear differential equation is finally generated as a difference ideal. And so that's the a more mathematical restatement of that theorem is
For
saying
example, it's going to be
that-
sigma is equal to 0, right?
the kernel
No, really. That's what you said.
of, okay, so let's choose n squared independent difference variables, and let's also, and put them into a matrix set, and let's also invert the determinant, and then you have a surjection onto the sigma picabis ring just by sending set to the fundamental solution matrix Y. Okay, so this is very close to being a difference polynomial ring in n squared variables. Just invert the determinant. And so if you want, I can recall what is the difference polynomial ring really.
Stupid for a moment.
Okay.
We define the Picard-Vecchio ring as the ring generated over K by the entries of Y.
Mm-hmm.
And now you seem to be saying that the matrix Y is an element of the ring R.
Okay, so this is really, maybe if you want, this is mapping set I,
Okay.
I, Y to
Okay,
like that.
okay.
I thought you were model theorist.
Oh,
Okay.
I see, it was a tuple. Well, no.
Yeah, so
Squared
C is
Matrix.
yeah,
The matrix.
it's n by n.
Okay, fine. Okay.
Okay. So the statement I want to make is that the kernel is finally generated as a difference ideal. So this is a morphism of difference rings, and so the kernel is a difference ideal, and the statement I want to explain the proof of is that this kernel is finally generated as a difference ideal. So that you can think of the sigma picabis ring. This is really the algebra that encodes all the difference algebraic relations among the solutions. And so really what are the relations? Well, the relations are really all those elements in the kernel. Okay, so this is really what we want to compute, this is really what we want to understand. We want to understand that kernel of that map, and I'm claiming that it is finally generated as a difference ideal. Okay. Okay, and some definition which has been proven to be really useful in that context is to say what it means for a difference algebra to be finitely presented, so let R be a K sigma algebra. So here K is just a difference field, and to say that R is a K sigma algebra just means that it's a K algebra equipped with an anamorphism sigma, which extends the given sigma on K. Okay, so R is a K sigma algebra, and then say that R is finitely sigma presented over K, so finitely sigma presented if there exists an isomorphism between R and the quotient of the difference polynomial ring modulo a difference ideal which is finitely generated. Okay, so if you can write R as a quotient of a difference polynomial ring in finitely many variables modulo a difference ideal that is finitely generated as a difference ideal, then we call R finitely presented. So this is really very similar to the notion of being finitely generated, finitely presented for algebras, right?
That's a sigma ideal.
Yeah, that's the
Sigma.
difference ideal generated by F1 to Fn. Yes.
So let me just try to understand this theorem. So one very special case of this theorem, and I guess the uniqueness thing for the Cartesian difference ring, is that whether or not this differential equation has a solution in sigma constants is somehow easy to read off, and if one fundamental solution is over the constants, then the other one would be too.
Could you repeat?
You're looking
Yeah, I
at
would-
second.
Okay, so say the property that Y,
Yeah.
this matrix,
Mm-hmm.
all of its entries are sigma constants.
Yeah, I see.
That would be reflected, obviously, in the different structure on the ring generated by Y.
Yeah. Mhm.
So what you're saying, for example, is that for this Y to be or not be constants
Mhm.
is almost entirely determined by the equation
Yeah.
rather than the particular solution. I guess up to possibly iterations of sigma.
Yeah, so I would say, so if Y is constant, it's in one R, it's definitely gonna be at least periodic in another R. So I would say if it's periodic in one R, it's gonna be periodic in another R.
And is it easy
Yeah.
to see from the matrix A where the solutions will be, whether you will be able to find sigma constant solutions?
I don't think so, like directly,
Okay,
I don't know. But,
okay.
Again, so what I was asking, what is the relation between R and functions? Are there any embedding theorems?
Mirror more.
yeah, I mean,
What,
so this uniqueness, like this is really just very abstract algebra.
Yeah.
This, like even you don't, like K is just any delta sigma field. You don't think about functions whatsoever. This is just, all is very algebraic, right?
But who cares
But
if it's all
if you have some,
I think.
if you have some very concrete field, okay, so if you have something like Kx, right? This is the case people care most about, right? So at least, I mean, there's like even Cx with, if you're acting just on X with the sigma as well, this is also interesting. Okay, but here, say like here, you can always, so K is the sigma field here. And so here the action of delta and sigma commute. And so here you can always find a solution, say you can always find a solution matrix in Laurent series. So
no, so
what?
1 over x, or sorry, 1 over 2x if the right hand side, so the solution is square root of x.
I think we already, let's discuss it afterwards. I think we actually already discussed it at some point. You can always, like,
It's analytic, it's fine.
At 0.
so you can, so just pick a regular,
Depends on where you
so pick, Alexei,
No.
pick a branch.
yep, pick a regular point. Pick a regular point for the differential equation and do it there. Don't do it at 0 if it messes it up.
That's exactly what I'm asking. So the other embedding theorems, like
There is a theorem stating over that delta sigma field K, there always exists a sigma Cartesian R inside that delta sigma field.
Right.
Okay?
That's what you're saying.
And inside there it's unique. There exists a unique sigma Cartesian ring
Right.
inside that delta sigma field extension. Okay? So if you're really concerned with more specific setups, there's something more specific that can be said. Okay, so if you're thinking of functions,
and
yeah, usually you're just working there.
And so that embedding is a differential difference embedding.
Yeah. And the proof is actually really easy. Okay. Okay, so let's get back to this thing here.
So what's your
So
Cartesian rings are always finitely sigma presented.
yeah, so that's exactly what I'm aiming for. So we want to show that sigma Cartesian rings are always finitely sigma presented. But yeah, but to be sure that this actually, so that this statement about sigma Cartesian rings actually gives us back the proof for this theorem. We need to know that actually any finite presentation, well actually, so we sort of need a lemma which says that any presentation of a finitely sigma presented K sigma algebra is actually a finite presentation. But let me put the lemma. So the statement is that if R is finitely sigma presented, so this really just means that there exists one such isomorphism. So there exists one surjective map from one polynomial ring, from one difference polynomial ring onto R, such that the kernel is finitely generated as a difference ideal. But what this lemma is saying now, that actually for any surjective map from a difference polynomial ring onto R, the kernel will be finitely sigma generated.
And this n is unrelated to the previous n?
Yeah, yeah. Mhm.
Okay.
Okay, and so knowing this, it will be sufficient to prove
So R,
that.
R here is a big addition.
Yeah.
But actually, it could be any finitely sigma presented.
Any finitely.
Yeah,
Okay.
but it's like we are concerned with R being the sigma Cartesian ring. Yeah. Okay, so knowing this, it suffices now to prove that the sigma Cartesian ring is finitely sigma presented. Okay. And maybe, so let me say a few words on the analogy. So this, you have this result as well for algebras, so for finitely presented algebras, this holds as well.
But not
Like,
differential algebra.
I don't know about differential algebra. I don't think a lot of, I wouldn't know actually any reference for finitely differentially presented differential algebras. So it's not,
Well,
I don't think much has been done
I
on
mean, the
that.
kernel of a differential algebra homomorphism is always finite, generally for a polynomial.
Of a
right?
radical differential ideal?
Ah,
Yeah.
radical.
Ah, that's a big difference.
Is the kernel always radical?
Beautiful.
The kernel is not always radical.
No.
Felix, so this has been known for differential algebra groups.
Who, where's the proof?
Oh, in my paper was Sergei and Henry Gillet, for example.
Thank you. With Gigi,
Yeah,
with
GGO.
Gillet.
Yeah, but the differential case is sort of way easier, I would
Just
think,
the
because it's really
In
about the radical, like in characteristic zero, all Hopf algebras are reduced, and then it's sort of, I think that's sort of the main
yes.
ingredient to get rid of the
I had
radical.
to prove that. That's right. For the parametrized Picabessio theorem.
That's precisely how the proof goes.
Oh, right.
So it's
Okay.
Okay, so let me say maybe very briefly something about the analogy. So what is known in general about algebras, about difference algebras being finitely difference presented. So in usual commutative algebra, if R is a finitely generated A algebra, then you know, of course, by Hilbert's basis theory, we know that R is finitely presented,
finitely presented.
and right?
R is finitely presented. Then it kernels.
Ah, right.
So,
Any
but-
kernel.
so you'd hope that you'd have a similar statement for difference algebras, but of course you know so that the analog of Hilbert's basis theorem in difference algebra is way weaker than we would hope it is. So it only says that extending chains of perfect difference ideals are finite.
Right.
And so, but there's some result in that direction. And the strongest I know is that if you assume that R is finitely sigma generated, and you also need to assume that it's an integral domain. Then one can show that there exists, say, an F, a non-zero element F in R, such that if you do the difference localization at F, then this is finitely sigma presented. Okay, so you need the assumption of an integral domain, and you need some localization to get there.
Meaning it is sufficient.
Yeah. I mean, that's it holds under this assumption.
And the localization, you have infinitely many denominators. Like you have.
Yeah, well, so you have all the, you apply sigma
Sigma.
to the denominator, yeah.
What's the significance of this F?
Well, so you can prove this using the like characteristic sets, and then this is some product of initials.
Yeah.
Okay, so if we want to prove that the sigma Picard theory is finitely sigma presented,
But before you do that, so are there actual examples showing that F has to be in the denominator and we have to have infinitely many equals?
also it's really hard to write down examples of prime ideals which are not finitely generated as difference ideals. So I was discussing this. So it's easy to write down an example of a difference ideal in the difference polynomial ring which is not finitely generated as a difference ideal.
Yeah.
And I was discussing this with Alexander Levin for some time. And so I have an example. So I have an example where I'm fairly sure it's. So I think I'm sure it's a prime ideal, and so I can write it down sort of, and so like the perfect difference ideal generated by the set of generators I can write down, and
Is it like
but it's hard to prove that it's not finitely generated as a difference ideal.
What does it mean hard to prove? You don't have a proof yet.
Yeah.
Okay.
But I have a candidate say, and yeah.
Is it similar to Ritt's example of the differential polynomial ideal? It's not finitely generated as a differential ideal.
Is it a prime ideal? Rick's
Yeah,
example is a
yeah.
prime ideal?
Yeah.
Okay. I don't think I know that
Oh,
example.
I'll send it to you.
Okay. Okay. Okay, so the idea to prove the statement that the sigma Picard theorem is finitely sigma presented is of course to use the sigma Galois theory. And then the main result there, which sort of connects the defining equations of the Galois group with the difference algebraic relations among the solutions, is really the torsus theorem. So the torsus theorem says that if you take the tensor product with the sigma Picard theorem twice, then this is the same as the tensor product of the sigma Picard theorem with the coordinate ring of the sigma Galois group. So over here k, with a little k, is the differential constant of the base field, and so G, here G is the sigma Galois group. L over K. And so this is, G is a sigma algebraic group. Okay, so if you want, I can give you some more details on the definition of G, but maybe for now it's enough to just know that this is a group defined by algebraic difference equations. It naturally comes with an embedding into GLN, and that's the algebraic reformulation of the dorsal theorem. Okay, you can think of spec of R as a dorsal for G. Okay, and so now here, if you localize at the non-zero divisors of R at the left side, what you find is that L, so we can replace on the left side R with L. So what we need to do is we need to bath from information. So if you want to bath from information on G to information on R, so which is basically information on the relations between the solutions, then really what you use is the dorsal theorem. And so this is saying that up to some field extension, those two rings contain the same information. Okay, so we need to have some.
So before, so going back, you were saying that you had an example in progress for which you don't know.
Well, I've not thought about it for years, but I've thought about it at some point.
And so the ideal that you had in mind, did it correspond to any differential equation or not?
No, it did not correspond to any differential equation.
So you're saying that you had an example in progress for a part of the theorem?
No, so I mean here, well, so that's the theorem. So the thing below here is just some general educational thing.
Okay.
Okay. I was curious about having so I think it's actually sort of clear that it exists an example of a prime difference ideal in a difference polynomial ring which is not finitely generated as a difference ideal. It's easy, yeah. So that's what I wanted to see, and I have a candidate, but didn't do all the details.
But the construction did not come from any,
It didn't come from any differential equation.
From any
No.
part of the Pythagorean construction.
No.
Okay.
This second general educational thing,
Mm-hmm.
is it obvious and it not?
It's not easy. So this uses the theory of characteristic sets.
Uh-huh.
So I mean that's the only proof I know of
Is
this.
it written down anywhere?
It's written in my lecture notes on what's the name? Called algebraic difference equation. Yeah.
But again, so the constructional deal was what? Artificial completely.
Well, yeah. Yeah.
Well, everything starting from the construction of real numbers in mathematics is completely artificial.
Okay. Let's go back to this. Okay. So we are comparing R and the coordinate ring of the difference algebraic group. So we'd like to have a lemma which ensures that extending the base field does not change the property of being finitely sigma presented. Okay, so we can actually pass from the coordinate ring of G to R, and okay, so that's exactly the lemma we need. So if R is a K sigma algebra, and if L over K is an extension of sigma fields, then R is finitely sigma presented over K if and only if when we extend the base field we are finitely sigma presented over L. Okay, so this direction is really easy, but
What's the relation between R and L?
so L is a difference field extension of K.
Yeah, but what is relation with R?
R is a K sigma algebra.
So there's no relation.
No relation. Yeah. We just do a base extension. So we base extend the base field. Okay.
Michael, by the
By
way,
L.
so for all your stuff, is it important that you have just one sigma? You don't have a. Where does it break?
Yeah, I mean, there's all these. But it just. So I think the fairest answer is it just hasn't been done. And well, especially in the thing that becomes your theory, I think there's some serious obstacles to uniqueness and existence in general.
But
if you have
assume,
several,
but if you assume
Yeah.
that suppose you
yeah, no, then there's no like the Galois correspondence and all that, and the definition of the sigma Galois group. I think that's perfectly fine.
And,
Yeah.
no, my question was not about that. Suppose that is done.
Yeah.
What about your theorem?
Oh, yeah, I believe it's true, but assuming that the sigmas commute. It's not true if you don't assume that the sigmas commute.
I mean, it's not true.
If you have several sigmas, if you have two sigmas which are not necessarily commutative, then you should be able to write down an example of a difference algebraic group such that the coordinate ring is not finitely sigma percent.
For any kind of non-commutativity, or maybe they commute up to something, then it's
Okay, if they commute up to something, so in terms of our, like for n times n, in terms with the notation of our paper, it's it will not be true. Oh no, yeah, no for the direct, yeah. Okay. Yeah, so for the commutative it will be true, but for the free product, it will not be true. But maybe if you have some relations, yeah, I wouldn't know the answer to the question for which actions of group, like for which groups is it always true that that the defining ideals of the groups are always finitely generated. Yeah. Yes.
If I read your lemma correctly, you're saying that given R and K sigma algebra, then R is finitely sigma percent over K, if and only for all L extension of K, I think confused, R tensor L is finitely sigma percent.
Oh yeah, that's
If and
true.
only if for some.
For some of all.
Yeah,
For some of
yeah, exactly.
But for some mean nothing because on the other side you already have K.
Yeah.
Okay, let's say it's for
Yeah.
all, right?
Yeah.
Yeah.
So I prove one direction, okay.
Yeah.
So it's some kind of is it has anything to do with disjointness?
Not really. I mean, here it's just formally here.
What's the other argument? What's the other
It's,
way?
I mean, it's really an easy lemma. I mean, it's like for algebras. Yeah. Okay. Okay, so
So
using
you're here making no assumptions on K and R?
so R is just a K sigma algebra, and I'm saying that R is so basically what this is saying that the property of being
Sigma prime.
finitely sigma presented is stable on a base extension.
Yeah.
Yeah, I mean you can go both ways. Like the important way is to go from here to here.
Yes.
That's more important. Yeah.
Yeah, of course. Otherwise the same presentation works.
Yeah.
I mean, suppose I take L to be the quotient field of R in case R is integral domain.
Yeah.
And how do you get it back over?
From from the thing
From
that
this
he's
side.
just erasing, that for an integral domain, all you need is one.
Is one over F.
Yeah.
Okay.
Okay, so now
Then in that case, the general thing would follow also that.
Let him do it.
Because the quotient field of R is inside any L extension.
Okay. So you knowing this and knowing this lemma, now we are reduced to proving that the coordinate ring